Greetings, fellow nerds. In previous videos, we've dissolved precious metals like platinum and gold using a mixture of hydrochloric and nitric acids. This mixture is so well known that it even has its own name, Aqua Regia or royal water. It's a very common reaction and still done by most labs working with those metals. It consists of a 3:1 molar ratio of hydrochloric acid to nitric acid, and this ratio is selected to maximize usage of all the acids. The mixture decomposes on standing to chlorine gas, nitrosyl chlorides, and various nitrogen oxides. You can see in the first reaction that nitric acid can oxidize up to 3 chloride ions, and that's why the ratio of 3 moles of hydrochloric acid per 1 mole of nitric acid is used. But the real fun begins when we react them with platinum and gold. Those metals are extremely resistant to most chemical attack, but will dissolve in the mixture of Aqua Regia. Interestingly enough, neither hydrochloric acid nor nitric acid will dissolve platinum or gold alone. You need both acids together. So that brings us to our video topic. How does Aqua Regia work? Why are those acids used in particular? And why do we need 2 acids, not just 1? Let's go through the science. Most metals are reactive all on their own. Iron will burn on air if thin enough, aluminum dissolves in hydrochloric acid, and sodium doesn't even need acid to react with water. All these reactions happen because the products are more stable than the reactants, and so the release of energy is what drives the reaction forward. But metals like gold and platinum are more stable as metals, at least on a terrestrial world like Earth. If we lived on a planet with a chlorine atmosphere, things might be different. But we're getting to that later. Anyway, gold and platinum don't dissolve in hydrochloric acid alone because the resulting metal chloride salts and hydrogen are actually slightly less stable. In fact, if you got the salts and heated them with hydrogen, you get the metals again. So we can't go in that direction. We need some extra driving force to rip the electrons out of the metal and convert them to ions. We need an oxidant. Nitric acid is that oxidant. It's strong enough to rip electrons from gold and platinum. It's also very convenient being a liquid and relatively easy to access for ancient alchemists first discovering it. Does this mean we can use other oxidants? Actually yes, chlorine gas. And in fact we've done this in a previous video. Chlorine gas is a powerful oxidant and when mixed with hydrochloric acid can dissolve platinum without the need for nitric acid. This is why I said earlier if we lived on a world with a chlorine atmosphere, we'd probably consider the precious metals not to be so precious. We'd also be dead. But anyway, this experiment shows that the nitric acid component of Aqua Regia is needed for its oxidative property, and can be substituted with a suitably strong oxidant like chlorine. Although most amateurs probably don't want to use chlorine gas due to it being a toxic gas. Are there any other oxidants we can test our hypothesis with? And as usual, it's not a Nerd Rage video without some sort of experiment. So we're going to make a new one and use the ultimate oxidant, electricity. The reaction is fairly simple. We get a solution of 30% hydrochloric acid and stick in 2 platinum electrodes. Now we just turn on the current to a density of 1 amp per square centimeter at a voltage of about 2 volts. It doesn't take long, but already the platinum metal is dissolving into yellow chloroplatinic acid. So this shows the importance of an oxidizer to make Aqua Regia work for dissolving precious metals. And it can be nitric acid, chlorine gas, or even electricity. There are even more like hydrogen peroxide, bleach, or sodium chlorate, but that's discussion for another time. By the way, this experiment also works with gold. I just didn't have any at the time of filming this video. Okay, so that explains why Aqua Regia needs nitric acid, but what about the hydrochloric acid? Why doesn't nitric acid work alone if it clearly has enough oxidation power and is also an acid? Alternatively, why not substitute the hydrochloric acid with sulfuric acid? Why doesn't sulfuric acid and nitric acid work to dissolve precious metals? The answer already lies in our previous electrochemistry experiments. Now those of you that have seen my videos know I like to use platinum electrodes for all kinds of electrochemistry, and we've seen it survive all sorts of extremely corrosive conditions. You've seen me electrolyze copper sulfate to make sulfuric acid and potassium chloride to make potassium chlorate. How come in those conditions it survives, but not hydrochloric acid? Like all electrochemistry, the answer is closely linked to reaction conditions. 30% hydrochloric acid is extremely concentrated in chloride ions. And these ions complex with any platinum ions to form hexachloroplatinate ions. It's this complexation that serves as a favorable driving force for the dissolution of platinum. Otherwise, the platinum ions just stay stuck on the surface of the metal and a competing oxidation reaction will occur. If I were to do this with sodium hydroxide, which doesn't form platinum hydroxide as easily, it could handle much higher currents before degrading. And I would get oxygen gas forming as the competing oxidation reaction rather than platinum dissolving. So by selecting hydrochloric acid, we favor the decomposition of the metal. Even under these relatively modest conditions of 2 volts, when we've done 5 volts and survived in sulfuric acid. Now those of you who've seen me make potassium chlorate are probably asking, why didn't those chloride ions destroy the platinum electrode? The answer is they do, but much more slowly because the pH is too high. Under non-acidic conditions, the reactions favor the formation of chlorates and hypochlorites over the dissolution of platinum. But it still happens. But if we lower the pH considerably by making it strongly acidic, as in the case of highly concentrated hydrochloric acid, then we favor the formation of hexachloroplatinate ions and thus dissolve the platinum. It is for this reason why the original Aqua Regia mixture of hydrochloric and nitric acids even has hydrochloric acid. The chloride ions complex with the metal and offer a driving force to dissolve them. So would sulfuric acid work? Actually, sulfuric acid and nitric acid does dissolve gold, but only barely, and you have to force it with strong heating. And it does not work with platinum. While platinum sulfate exists, sulfate is just not as good a complexing agent. So a mixture of sulfuric and nitric acid works extremely badly dissolving platinum. This also explains why nitric acid alone is not sufficient to dissolve gold and platinum. Nitrates are also not strong enough complexing agents to stabilize the metal ions alone. This is not to say that gold and platinum nitrates don't exist. They do, but they must be made indirectly using other reagents and not through direct reaction of the metal with nitric acid. At this point you may ask, would another acid form a metal complex and work to dissolve it along with nitric acid? Indeed yes, a hydrobromic acid can be used in place of hydrochloric acid and dissolve precious metals, including platinum. But since hydrobromic acid is more expensive and less common than hydrochloric acid, this reaction is very rarely done. So there you go, that's why we need both hydrochloric and nitric acid to make Aqua Regia and dissolve precious metals. What we really need is a strong oxidizing agent to provide the energy necessary to rip electrons from the metal, and a strong complexing agent to form complex ions with the metal and dissolve them from the surface into solution. Aqua Regia is a cheap and convenient mixture that provides both of those chemicals. I hope this video was interesting. Thanks for watching. Special thank you to all of my supporters on Patreon for making these science videos possible with their donations and their direction. If you're not currently a patron but would like to support the continued production of science videos like this one, then check out my Patreon page here or in the video description. I really appreciate any and all support.